Differentiation. Differentiation has something to do with gradient. Gradient is the measure of the steepness of a slope. Here are 4 examples. Slope A has positive steepness. Slope B has negative steepness. Slope C has 0 steepness. Slope D has a larger steepness compared to slope A. In general, to find the gradient of a line, we require 2 points and apply the following formula. But how do we find the gradient of a point on a curve, such as the following? We draw a line that passes through only that point on the curve. We call this line the tangent line. And the gradient of the point on the curve is equal to the gradient of this tangent line through that point. As mentioned before, to find the gradient of a line, we require 2 points and apply the formula for gradient. In this case, the gradient at the point x equals to 1 on the curve y equals to x squared is 2. Here comes the big question. Can I find the gradient of any point on a curve without drawing a tangent line? There is a way. Let's use the same example of finding the gradient at the point x equals to 1 on the curve y equals to x squared. Instead of drawing a tangent line passing through the point x equals to 1, I choose another point on the curve, such as the following. Next, we draw a straight line passing through the 2 points. We hope that the gradient of this line is almost equal to the actual gradient of the curve at x equals to 1. If we apply the formula for gradient, we find that the gradient of this line is 2.67, which is actually quite close to the actual value of 2. Now, let's try with a different point which is closer to the point x equals to 1 on the curve, such as the following. Then, we draw a straight line passing through these 2 points and find the gradient of this line. If we apply the formula for gradient, the gradient of this line is 1.67, which is even closer to the actual value of 2. What can we deduce? If we want to find the true gradient of the point x equals to 1 on the curve, we should bring the second point as close as possible to the point x equals to 1. Let's do this algebraically. Let's choose a point which is very close to 1. Let's call this point 1 plus a, where a is a very small number. Now, if x is 1 plus a, what will be the corresponding value of y? We simply substitute x equals to 1 plus a into the equation of the curve, which is y equals to x squared. We will get 1 plus a squared. Next, we draw a straight line passing through the 2 points and apply the formula for gradient. We obtain the following. Expand the expression and we obtain 2 plus a for the gradient. Now, what value of a will make the gradient of this line exactly equal to the actual gradient? We know that the approximation of the gradient becomes better if we bring the second point as close as possible to the first point. Therefore, why not we bring the 2 points together? If we bring the second point to exactly where the first point is, the 2 points will therefore have the same coordinates. Hence, a is 0. Therefore, when a is 0, the gradient becomes 2, which is exactly the actual gradient of the point x equals to 1. Wow! Now, let's think back about the steps to find the gradient of a point on a curve without drawing a tangent line. Please pause the video now to fully appreciate what we have been doing up till now. We have been focusing on finding the gradient at the point x equals to 1 on a curve. How about the gradient of other points on the curve? Now, let's focus on finding the gradient of the same curve y equals to x squared at the point x equals to 2. Let's apply what we have learned. The first thing is to locate another point on the curve. Let this point be 2 plus a. Therefore, the corresponding value of y will be 2 plus a squared. Next, we draw a straight line passing through the 2 points and apply the formula for gradient of a line. We get the following algebraic expression. So, how do we make this gradient of the line exactly equal to the actual gradient of the point x equals to 2? The actual gradient of the point on the curve is obtained when the 2 points coincide. In other words, when a equals to 0. Therefore, the gradient of the point x equals to 2 is 4. Now, if we were to do the same thing on other points on the curve, for example, x equals to 3 and x equals to 4, we will discover that their gradients are 6 and 8 respectively. If you were to study the table very carefully, you will realize that the gradient follows a pattern, such as the following. The gradient actually has an expression of the form 2x. Now, what do you think will be the expression for the gradient of other curves, such as the following? Let's focus on the curve y equals to x cubed, and let's find the gradient at the point x equals to 1. We are going to apply the same steps as before. First, we choose a point very close to 1. We let this be 1 plus a. The corresponding value of y will therefore be 1 plus a cubed. Next, we draw a straight line passing through the 2 points and find the gradient of this line. We apply the formula for gradient of a line and obtain the following expression. The actual gradient is obtained when the 2 points coincide. In other words, when a equals to 0. Therefore, the gradient at x equals to 1 of the curve y equals to x cubed is 3. If we were to find the gradient of other points on the curve y equals to x cubed, we obtain the following result. If you study the values of the gradient very carefully, you will discover that they follow the following pattern. And we conclude that the expression for gradient of the curve y equals to x cubed is 3x squared. This is what we have discovered so far. Study this table carefully. What do you think will be the expression for the gradient of the curve y equals to x power 4? If your answer is 4x cubed, then you are right. Let us now generalize this. If you are given a curve y equals to x power n, its gradient is simply n times x power n minus 1. This process of obtaining the gradient expression from a curve y is called differentiation. Differentiation is a very powerful mathematical tool. Let me use this example to demonstrate. Suppose we are to find the gradient of the function y equals to x power 100 at the point x equals to 1. If we were to do this the long way, we find that it's going to involve a very tedious expansion. But differentiation tells us that if we are given the equation y equals to x power 100, its gradient is simply 100 times x power 99. And to find the gradient at x equals to 1, we simply substitute x equals to 1 into the gradient expression and we obtain 100. Please note that n can be 0, integers, fractions, decimals, and it can also be negative. Now, I am going to introduce a symbol for the expression for gradient. The symbol is d over dx of y. The symbol d over dx is called a differential operator. As the name suggests, it is just an operator that performs differentiation. To be more precise, the operator d over dx performs a differentiation operation on the function y to produce its gradient expression. In words, d over dx of y is simply differentiate with respect to variable x the function y. Please note, d over dx of y has the same meaning as dy over dx. So, what have we learned so far? If you are given the function y equals to x power n, and when you are told to find dy over dx, it simply means you are to find the gradient of y. In this case, it's n times x power n minus 1. Please note that this is just the beginning. More complicated expressions will come. No matter what, do not forget the true meaning of differentiation, which is a method of finding gradient of a curve without drawing a tangent line.